All right, hey everyone, welcome to the Exam 2 walkthrough. I'm just going to take this time, go through one problem at a time. I'm not going to edit out any mistakes. We'll see how quickly I can do this. So first things first, as always, we're going to write our name, because it's the first thing you do on an exam. All right. So for question number 1, we're going to use the product, quotient, and or chain rule to calculate the derivatives for the following functions. So let's take a look at A. Here on A we have two functions of x multiplied together, and if we see multiplication, that should say we use the product rule. So the product rule, of course, is LDR plus RDL. And here our left-hand thing is 2x cubed plus x. Our right-hand thing is x squared minus 1 cubed. So our DL, the derivative of this left-hand side here, is 6x squared plus 1. And dr, the derivative of this right-hand thing. Here we have to use the chain rule, but we find 3x squared minus 1 squared times 2x. So if we throw all those together, LDR plus RDL, we get 2x cubed plus x times dr, which is 3 times x squared minus 1 squared times 2x, plus RDL. So that's x squared minus 1 to the third power times DL, 6x squared plus 1. So that's your answer for A. And for B, we have a fraction of stuff, so that tells us we're going to use quotient rule. So quotient rule, Bodito minus Todibo over Bobo. So let's write those things out. The bottom is x minus 1. The top, we have this multiplication, x plus 3 times x to the 4th plus 3x squared. To find the derivative of the bottom, well, it's pretty easy, it's just 1. And to find the derivative of the top, we have to use product rule. So let me change colors here. Product rule again is LDR plus RDL. So our left-hand thing is x plus 3. Our right-hand thing is x to the 4th plus 3x squared. And so DL is, again, 1. DR is 4x cubed plus 6x. So if we throw all those together, we find that dTo, the derivative of the top, using the chain rule, we get LDR plus RDL. So that's x to the 4th plus 3x squared times DL, which is 1. So if we throw our Bo, Dbo, Dto, etc. All together, we get x minus 1 times, and now this has to all be in parentheses, the derivative of the top, which is x plus 3 times 4x cubed plus 6x plus x to the 4th plus 3x squared times 1, close parentheses. These parentheses here are important. Without them, if these parentheses weren't here, we would just have x minus 1 times this stuff. It's also important that we have x minus 1 times that thing over there. So that's what the parentheses are for. So that is our Bo Dto. I'm running out of room, so I'm going to move this over here. So that's our Bo Dto. Now we need our minus Todibo. So minus x plus 3 times x to the 4th plus 3x squared. So that's To. Dbo is just 1. And then lastly, Bobo. And that is our derivative for B. Moving on, we want to find g double prime of 2 if g of x is 4 times 3x plus 11 to the 1/3. So step 1, of course, as always, find the derivative. Here, this is a classic chain rule example. So we bring down the exponent and multiply times, we copy and paste the inside, and then we subtract 1 from the exponent, so that's going to give us minus 2 over 3, and then we multiply by the derivative of the inside here, which is just 3. And now we get some nice cancellation, because 3 times 4/3 is just 4. So this becomes 4 times 3x plus 11 to the minus 2/3. And now we can take the second derivative. G double prime of x is, when we bring down this exponent here and multiply, gives us minus 8 over 3. We copy and paste what's in parentheses. We subtract 1 from the exponent, so that gives us a minus 5/3 in the exponent. And then we're going to multiply by the derivative of the inside, which is just 3. And again, just like last time, we get some nice cancellation here. So we end up with minus 8 times 3x plus 11 to the minus 5/3. Now that we have our second derivative, we can plug in 2. And so we have 8 times 3 times 2 plus 11 to the minus 5/3. And this is minus 8 times 17 to the minus 5 over 3. And I'm happy with that. If you convert that to a decimal, it's something like minus 0.071, something along those lines. I forget the exact number. But this is kind of the thing I'm looking for. But I'm more than happy if you convert this to decimal. All right, let's take a look at number 3. So for number 3, we want to find the points where the second derivative of this given function is 0. So that means we're going to find the second derivative and set it equal to 0. Before we find the second derivative, we have to find the first derivative, which we'll find is 6x squared minus 6x minus 12. The second derivative is 12x minus 6. We're going to set this equal to 0. So this tells us that 12x equals 6, so x equals 1/2. And this is what I was looking for, was x equals 1/2. If you went back and plugged it into the original function, and you found f of 1/2 equals 2 times 1/2 cubed, minus 3 times 1/2 squared, minus 12 times 1/2 plus 5. So f of 1/2 equals 2 times 1 over 8 minus 3 times 1 over 4 minus 6 plus 5. So this is 1/4 minus 3/4 minus 1, because this minus 6 plus 5 combines to be minus 1. So this is 1/4 minus 3/4, well, that's minus 2/4 minus 1. So that's minus 1/2 minus 1, so that's minus 3/2. So we have 1/2 comma minus 3/2. Granted, that being said, I still gave full credit for just the x value. All right. For number 4, we want to find the equation of the line tangent to the curve 3x squared plus 6y squared equals 27 at the point 1, 2. So if we are ever finding the equation of a line tangent to the curve, that tells us we're probably going to use point-slope form, and we're probably going to need a derivative. So point-slope form again, y minus y1 equals m times x minus x1. But the slope here, we're looking for the equation of a tangent line, so the slope is the derivative. So it's dy dx, or f prime of x, something along these lines. And so in this case, let's find dy dx. So we're going to take the derivative of both sides of this equation with respect to x. Okay, well this is 0, right? The derivative of a constant is always 0. And now we can go term by term over here. This first term, when we take its derivative, the variable here is x. The variable of integration is, the variable of differentiation is x, so we're taking the derivative with respect to x. And since this variable and this variable are the same, we just apply our rules like normal. We get 6x. Here we have something with a y in it, notably not an x, and we're taking the derivative with respect to x. What does that mean? Well, that means we take the derivative like normal, but then we multiply by dy dx. Okay? And that's good, because now we have a dy dx. That's what we're looking for. That's going to be the slope of the tangent line. From this equation here, we can subtract 6x from both sides. We get 12y dy dx equals minus 6x, and then we can divide both sides by 12y. So dy dx equals minus 6x over 12y, which simplifies to minus x over 2y. What this means, the fact that this is dy dx, means that on this curve here, if you give me an xy pair, I can plug in the x and the y here, and that will tell me the slope of the tangent line. Here's an xy pair. Let's plug those in. Let me erase that. So we're going to find that at our given point, dy dx equals minus 1 over 2 times 2. That's minus 1/4. So that is our slope. So we know that the equation of our tangent line will be y minus y1 equals minus 1/4 times x minus x1. But again, we're given that x equals 1 and y equals 2. Right there. So let's plug those in, and we get y minus 2 equals minus 1/4 times x minus 1. And that's our answer for that. All right, number 5. X and y are both functions of t such that x times y equals 4. We want to find dy dt when x equals 11 and dx dt equals 1. So we're looking for dy dt. That means we need to take the derivative with respect to time. Right, because we're trying to find the dy dt that should take derivative with respect to time. Perfect. So let's take d dt of both sides. All right, well, the derivative of a constant is always 0, so that's easy enough. Here, we have x and y multiplied together. But what are x and y? They are both functions of time. They both change over time. And so we have two functions of t multiplied together, and we're taking the derivative. That means we have to use the product rule. So our left-hand thing is x. Our right-hand thing is y. dl, remember we're taking the derivative with respect to t, and we're taking the derivative of a thing that is not t, a variable that is not t. So what does that mean? Well, we apply our standard differentiation rules. We get a derivative of 1, and then we multiply by dx dt. All right, we have a 1 dx dt. No need to write the 1. We can just say the derivative of the left-hand thing is dx dt. By similar reasoning, the exact same explanation tells us that dr, the derivative of the right, is dy dt. Because y is a function of time, we're taking the we're taking the derivative of the variable y with respect to t. So altogether, on this left-hand side, the derivative becomes L dr, so x times dy dt plus r dl equals 0, because the derivative of a constant is 0. We are given that x equals 11 and dy dt equals 1. Or sorry, dx dt equals 1. So we have 11 times dy dt, the thing we're trying to find, plus y times dx dt is 1 equals 0. So we have 11 dy dt plus y equals 0. So this tells us that dy dt equals minus y over 11. And we're almost done. But we can get a value of y. How? Well, we know that whatever x is, x times y is always going to be 4. And we also know that x equals 11. So xy equals 4, x equals 11, so 11y equals 4, so y equals 4 over 11. So let's plug that in here. And we find that dy dt is minus 4 over 11 over 11. Okay? And now we have a fraction on top of a fraction, because this is kind of 11 over 1. So this works out to be minus 4 over 11 times 11, or 121. So that's dy dt there. A cube starts with edges that are 1 inch long. The edges start to grow at a constant rate of 5 inches per second. How quickly is the volume changing when the edges are 11 inches long? All right, what information do we need to know? Well, we know that the edges are growing at a rate of 5 inches per second. So that means dE, I guess we can call it. The rate of change of edges with respect to time is 5. And our goal is to find how quickly the volume is changing. So that means our goal is find dV dt. And specifically, we're going to find it when the edges are 11 inches long. So that tells us that E equals 11. What equation relates volume of a cube to its edge length? Well, volume is just E cubed. Okay, where E is the length of the edges. So that tells us if we differentiate both sides with respect to t, the left-hand side becomes dV dt. And the right-hand side, the E cubed, we take its derivative with respect to t. We take the derivative like normal, we get 3e squared, but then we multiply by dE dt. And then we plug in our givens. So this is equal to 3 times 11 squared times 5, which works out to be 1815. And I suppose if you want to put units, that's inches cubed per second. In hindsight, E probably isn't a great variable name to use. Probably should have used X, because E is a given number. But we'll learn more about that. Don't worry about that right now. I probably shouldn't have said anything, but I'm not editing out mistakes. Here we go. Number 7, we want to find the intervals on which this given function is increasing or decreasing. Finding intervals which were increasing and decreasing, that means we're going to take the derivative, set it equal to 0, and find where it's undefined, use those points to break up the number line, and then test points from those intervals. But first things first, we got to take the derivative. We're going to get x cubed minus 8x squared minus 20x. And we're going to set this equal to 0. We don't have to worry about this derivative ever being undefined because it's a polynomial, which is defined everywhere. So we set this equal to 0. What can we do? Well, we can factor out an x because each term here has an x in it. If we factor out an x, we get an x times x squared minus 8x minus 20 equals 0. And this guy here factors to be x times x minus 10 times x plus 2. So these three things multiply to give us 0, and that can happen if and only if one of the things is 0. So that happens if either x equals 0, or x equals 10, or x equals minus 2. With this in mind, we get the following intervals. We get an interval from minus infinity to minus 2. We get an interval from minus 2 to 0. We get an interval from 0 to 10. And we get an interval from 10 to infinity. And now we're going to pick a number out of each of these. So I'll pick minus 3, minus 1, 1, and 20, I guess. And we're going to plug these into the first derivative. And that's going to tell us if the function is increasing or decreasing on these intervals. So f prime of minus 3 equals f prime of minus 1 equals f prime of 1 equals, and f prime of 20 equals. And I'll be honest, I don't know what these are off the top of my head. And so I'm going to plug it into a calculator. We can all watch me plug it into a calculator together. So if f of x, our given function again is equals 1/4 x to the 4 minus 8/3 x cubed minus 10 x squared plus 15. We want to find f prime of minus 3. We want to find f prime of, what was the number I said? Minus 1. We want to find f prime of positive 1. and we want to find f prime of 20. So let me write these numbers let me write down these numbers right quick. All right, and we're back here. So let me move that mouse pointer. We find that f prime of minus 3 is less than 0, f prime of minus 1 is bigger than 0, f prime of 1 is less than 0, and f prime of 20 is bigger than 0. So that tells us that f is decreasing on the intervals where it's less than 0. So it's decreasing on minus infinity to minus 2 and 0 to 10. And f is increasing on the places where the derivative is bigger than 0. So that's the interval from minus 2 to 0 and the interval from 10 to infinity. All right. Number 8, we want to find the absolute maximum and minimum of f of x equals x to the 4th plus 4x minus 3 on the closed interval from minus 2 to 2. So let's remember that on a closed interval, we always have an absolute maximum or a minimum. Why is that? That's kind of a good question. To answer that, let's take a look at a function that normally doesn't have a absolute maximum or minimum, just y equals x. So clearly this doesn't have an absolute maximum or minimum because, any point on this graph, you can always go to the right and you're going to get like a bigger output. But if we change it to be on a closed interval, so minus 2 less than or equal to x, which is less than or equal to 2. Cool. So now this function is defined on the closed interval between minus 2 and 2. Well, now it has an absolute maximum because at the endpoints, you can't walk to the right. You can't scoot your point to the right and find a bigger output value. So this is why a continuous function on a closed interval always has an absolute maximum and an absolute minimum, because it's bounded. There's only so many x values you have. You can't continue to keep plugging in bigger and bigger x values. Your x values are bounded. And so your output values will also be bounded if you have a continuous function. All right. Anyway, the way we find absolute maximum and minimum on a interval is we find the critical points. So let's do that right quick. F prime of x is 4x cubed plus 4. We're going to set that equal to 0 because that's where the critical points happen, where the first derivative is equal to 0. And from here we can pull out a 4. So 4 times x cubed plus 1 equals 0. If we divide by 4, this tells us that x cubed plus 1 equals 0. Tells us that x cubed equals negative 1. And we can take the cubed root of both sides, because we can totally take the cubed root because it's an odd thing. We can take the third root of a negative number. This tells us that x equals negative 1, because minus 1 cubed is minus 1. So that's our critical point. Once we have a critical point, and we know our endpoints, we test those by plugging them into the original function. Why the original function? Well, it's because we're guaranteed to have an absolute maximum and an absolute minimum. Our goal is just to find where they are. And they always happen either at critical points or endpoints. So once we have it narrowed down to 3 possibilities, we can just see which one is the biggest, which one is the smallest. And this is a job for a calculator. Good thing I have the internet. Yeah, leave. All right. So our given function is f of x equals x to the 4th plus 4x minus 3. We want to find f of minus 2, f of minus 1, and f of 2. So clearly, the biggest output of all of these is positive 21. All right, and that happens at f of 2, so that tells us that the point 2, 21 is our absolute maximum. And the smallest output is minus 6. Heck, it's the only negative one. So that tells us that at x equals negative 1, we have an absolute minimum. So let's write that out. we're going to say that the absolute min is at -1, -6, and the absolute max is at 2, 21. And one last problem here, number 9. A company that makes GameCube controllers has determined that, I should say that the cost, that the cost from producing X controllers can be modeled by C of X equals X squared over 1,000 plus 1,250. The controllers sell for $5 each. We want to determine the revenue function and the profit function, and we want to know how many controllers should be produced or sold in order to maximize profit. So let's start with revenue function. In general, a revenue function R of X equals X times price. So in our case, it's going to be 5X because the price is $5 each. And a profit function, P of X, is always just the revenue minus the cost. So our profit function will be 5X minus, and this should be in parentheses because we're subtracting the entire cost function, 5X minus X squared over 1,000 plus 1,250, which now we can distribute out the minus sign. We get our profit function as 5X minus X squared over 1,000 minus 1,250. Our goal is to maximize the profit. And when I say maximize, you should hear take the derivative, set it equal to 0. So our derivative is P prime of X equals 5 minus 2 over 1,000X, just bringing down the exponent here and subtracting 1. But 2 over 1,000, that's the same as 1 over 500. We're going to set that equal to 0. And so we can subtract 5 from both sides. We get minus 1 over 500x equals minus 5. Multiply both sides by minus 500, and we find that x equals 2,500. And so that means we need to produce and sell 2,500 controllers in order to maximize our profit. I hope this was helpful. Any feedback is appreciated.